Welcome to our deep dive into the quantum world.
Yeah.
You've given us selections from Akira Tonomura's book, The Quantum World Unveiled by Electron Waves.
Uh-huh.
And I can already tell this is going to be a fascinating journey.
For sure.
We're going to be using electrons to explore the bizarre realm of quantum mechanics and, get this, actually visualize magnetic lines of force inside a magnet.
Right.
It's something even Faraday couldn't do with his iron filings.
That's right. Yeah.
Okay, so
Yeah.
everyone remembers those classic images of iron filings arranging themselves around a horseshoe magnet, right?
Yes.
That's how we traditionally visualize magnetic field lines. But those iron filings only show us the lines outside the magnet.
Exactly.
They can't penetrate the material itself to reveal what's happening inside.
Uh-huh.
So how do we get past that limitation?
Well,
I'm guessing this is where electrons and their wave-like behavior come in.
precisely.
So we're using a tool we might not expect, electrons,
Right.
to reveal something hidden. This is like using X-rays to see inside the human body, but on a much smaller scale.
Yeah. Yeah.
What's fascinating is that we're harnessing something as seemingly simple as an electron
Uh-huh.
to unlock the secrets of magnetism.
And to really grasp how this works,
Okay.
we need to dive into one of the most mind-bending concepts in quantum mechanics. Wave-particle duality.
Wave-particle duality.
Yeah,
Now, this is where things start to get really interesting.
for sure.
It's the idea that things we think of as particles, like
Right.
electrons, can also behave like waves. Right.
Exactly.
It's a concept that challenges our everyday understanding of how the world works.
It really does.
I vaguely remember learning about the double-slit experiment in physics class.
Oh, yeah.
Wasn't that the classic example of wave-particle duality in action?
Absolutely.
It's considered one of the most beautiful experiments in physics.
It is.
Imagine you have a barrier with two tiny slits,
Okay.
and you fire electrons at it, one at a time,
Uh-huh.
one at a time.
One at a
So it's not like a continuous stream of electrons.
Nope, just one electron at a time.
Now, if electrons were only particles, you'd expect them to go through one slit or the other,
Right.
creating two distinct bands on the screen behind the slits.
You would think so.
But that's not what happens.
Yep.
What happens instead?
Well, you get an interference pattern, a series of light and dark bands,
Okay.
just like you'd see with waves interfering with each other.
Interesting.
And what's remarkable is that each electron, even though it's sent individually,
Yeah.
somehow interacts with both slits,
Hold on.
creating this wave-like interference pattern.
So each electron goes through both slits at the same time.
Oh,
My brain is struggling to wrap itself around this concept.
I know, right?
It's one of those things that's hard to visualize.
It is.
So each electron is somehow in two places at once.
Essentially, yes.
That's the mystery at the heart of quantum mechanics.
It is.
It suggests that things can exist in multiple states simultaneously, a concept that completely contradicts our everyday experience.
Absolutely.
Even the great physicist Richard Feynman said that the double-slit experiment contains the central mystery of quantum mechanics.
Yeah, he did.
Okay, so things can be in two places at once.
Mhm.
It's official. Quantum mechanics is officially weird.
It's a weird, weird world.
But how do we harness this bizarre wave nature of electrons to actually see things?
Right.
That's what I'm really curious about.
That's where electron holography comes in.
Electron holography.
It's a two-step process that allows us to visualize things at the microscopic level
Okay.
using the wave nature of electrons.
Okay, walk me through it.
Sure.
How do you create a hologram with electrons?
First, you create an electron hologram,
Okay.
which is essentially a recording of the phase information of electron waves that have interacted with an object.
Phase information.
Yeah.
I'm not familiar with that term.
Think of it like this.
Okay.
When two waves meet,
Mm-hmm.
if their crests and troughs line up perfectly, they reinforce each other.
Yeah.
If a crest meets a trough, they cancel out. This relative alignment of crests and troughs is what we call phase.
Okay, so it's about how the waves line up.
Exactly.
Yeah.
And the phase of an electron wave carries information about the object it interacts with,
Uh-huh.
like tiny variations in electric or magnetic fields.
So we record this phase information in an electron hologram.
Right.
What's the next step?
We use a light beam to reconstruct an image from the hologram.
Hmm.
This image contains both intensity and phase information, giving us a much richer picture of the object
Okay.
than a standard electron microscope image.
So it gives us more information.
Exactly.
This electron holography technique seems incredibly complex.
It is pretty involved.
I'm curious, where did this idea originate?
Believe it or not,
Yeah.
the concept goes back to the 1940s with Dennis Gabor,
Dennis Gabor.
the same person who later invented the hologram you see on credit cards.
Wow, the holograms on my credit card are connected to electron waves.
Yep. It all boils down to the same principle, using wave interference to record and reconstruct images.
That's pretty amazing.
Gabor was initially trying to improve the resolution of electron microscopes,
So that was his goal.
but he was limited by the technology available at the time.
I see.
One of the key challenges was the lack of coherent electron beams.
Coherent electron beams.
Yeah.
What makes them so important?
Coherent beams are like lasers for electrons.
Oh.
They produce highly focused monochromatic electron waves, which are essential for electron holography to work effectively.
So you need these focus beams.
Imagine trying to create a hologram with a jumble of uncoordinated waves.
Yeah.
You'd end up with a blurry mess.
Gotcha. So coherence is key.
Yeah.
But if Gabor didn't have access to coherent electron beams back in the 40s,
Right.
how did he create those early electron holograms?
He managed to create some rudimentary holograms, but their resolution wasn't great.
So not very sharp.
The real breakthrough came later with the invention of lasers.
So lasers help to advance electron holography.
Absolutely.
Okay.
Scientists realized that the principles of laser holography could be applied to electrons.
Interesting.
However, they still faced a major hurdle: producing those elusive, coherent electron beams.
So it's like having a Ferrari but no keys.
Exactly.
So who finally provided those keys and unlocked the full potential of electron holography?
It was a brilliant physicist named A.V. Crew.
A.V. Crew.
He was determined to see single atoms
Wow.
and believed that electron microscopy was the key.
Okay.
However, the existing electron microscopes weren't powerful enough.
I see.
They used beams of electrons produced by heating a filament, called thermal electrons,
Okay.
but these weren't bright or focused enough to achieve his goal.
What do you mean by bright when referring to electron beams?
Brightness in this context refers to the number of electrons packed into a small area and how tightly focused their paths are.
So it's about how concentrated the beam is.
Exactly. A brighter beam means a sharper image.
Gotcha. So Crew needed a way to create a brighter, more focused electron beam.
Precisely.
Okay.
His solution was to develop something called a field emission electron gun,
Field emission electron gun.
which extracts electrons from a sharp metal tip
Okay.
using an incredibly strong electric field.
It sounds like he was trying to squeeze electrons out of a tiny needle.
You're not far off.
And the most fascinating part is that this field emission gun relies on a phenomenon called quantum tunneling.
Yeah.
Quantum tunneling.
Quantum tunnel.
That sounds like something straight out of a science fiction movie.
It's a truly bizarre concept. Imagine you have a wall
Okay.
and you throw a ball at it.
Right.
In classical physics, the ball either has enough energy to go over the wall or it doesn't.
Exactly.
There's no way it can just magically pass through the wall, right?
Right.
But in the quantum world, particles can sometimes tunnel through barriers, even if they lack the energy to go over them.
Really? So they just kind of slip through?
It's one of the most counterintuitive predictions of quantum mechanics.
That is mind-blowing.
It really is.
So Crew's field emission gun is using this quantum tunneling effect to extract electrons from a metal tip.
Precisely.
By applying a strong electric field to the tip, he made the barrier at the surface of the metal incredibly thin.
That's right.
And because of quantum tunneling, some electrons inside the metal could tunnel through this barrier and escape into the vacuum.
Exactly.
So he essentially used a sharp metal tip and quantum mechanics to create a super bright electron beam.
Precisely.
It's incredible to think that something so seemingly simple could have such profound implications for science.
Crew's invention revolutionized electron microscopy.
Okay.
His field emission gun enabled the creation of brighter and more coherent electron beams than ever before,
Wow.
opening up new possibilities for scientific exploration.
It sounds like he finally found those keys to the Ferrari.
He did.
Now,
Yeah.
let's shift gears a bit. Why are we so interested in visualizing these magnetic lines of force inside magnets in the first place? What makes this so important?
It's not just about satisfying our scientific curiosity.
Right.
Seeing those lines of force directly allows us to study the behavior of magnetism at a fundamental level.
Oh, yeah.
It helps us understand how magnetic materials work, how they store information, and how they interact with other materials.
So it has practical applications as well.
Absolutely.
The-
These insights could lead to advancements in data storage, magnetic sensors, and even medical imaging. But perhaps even more importantly, by visualizing magnetic lines of force, we're getting a glimpse into the quantum world itself.
Right.
Where the rules are fundamentally different from our everyday experience.
Okay, now you've piqued my curiosity. What are some specific examples of how scientists have used electron holography to visualize these magnetic lines of force?
Sure.
What did they actually see?
Tonomura gives some fascinating examples in his book. One that stands out is the case of a recorded magnetic tape.
Recorded magnetic tape?
Remember cassette tapes?
Vaguely.
Well, think about how they work. You have a magnetic head that records information by changing the orientation of tiny magnetic domains on the tape.
Right.
Using electron holography.
Okay.
Scientists were able to actually see those magnetic domains.
Oh, wow.
And the patterns of magnetic lines of force they create.
So they could see those tiny magnetic regions.
They even observed swirling vortices.
Vortices?
Where those lines of force collide.
Like little whirlpools.
Exactly. And these vortices are a direct result of the way magnetic lines of force behave at the microscopic level.
Interesting.
They swirl and eddy when they encounter obstacles.
Right.
Similar to a fluid.
So something as seemingly simple as a cassette tape reveals this incredibly complex world of magnetic structures when we look closely enough.
Exactly.
It's mind-blowing.
It is.
Did Tonomura explore other examples?
He also looked at magnetic lines of force inside tiny particles. That's where we see another key principle at play.
Okay.
The tendency of magnetic lines of force to form closed loops to minimize their energy.
So it's like nature is being efficient and finding the shortest path possible. That's the amazing thing about visualizing these lines of force.
Right.
We're not just seeing pretty patterns.
No.
We're observing the fundamental rules that govern the behavior of magnetism at the most basic level.
It's like cracking a secret code.
It is.
But instead of unlocking a message, we're unlocking the secrets of the universe itself.
I have a feeling we've only just scratched the surface of what Tonomura uncovered in his explorations of the quantum world.
You're absolutely right. He didn't stop at visualizing magnetic lines of force.
He didn't.
He also delved into one of the most baffling predictions of quantum mechanics, the Aharonov-Bohm effect.
Okay, I'm ready for more quantum weirdness.
All right.
Bring it on.
Let's do it.
What is the Aharonov-Bohm effect? And why was it so controversial?
Well, the Aharonov-Bohm effect is this crazy idea that electrons can be influenced by magnetic fields even when they don't pass through them.
Hold on a second.
Yeah.
That sounds impossible.
I know, right?
It's like saying I can get a sunburn even if I never step outside.
It does seem to defy common sense.
Yeah.
And that's why when it was first proposed, it caused quite a stir in the physics community.
I can only imagine.
Yeah.
So how does it work?
Yeah.
How can something influence an electron if it's not directly interacting with it?
To understand that, we need to talk about vector potentials.
Vector potentials.
They're mathematical quantities related to magnetic fields.
Okay.
But they have a rather peculiar property.
Let me guess. They're not limited to the region where the magnetic field actually exists.
You got it.
Okay.
Vector potentials can extend beyond the physical boundaries of a magnetic field.
So they kind of like...
Think of it like this. Imagine a whirlpool in a river.
Okay.
The water is swirling in a specific region, but the influence of that whirlpool can be felt further out.
Okay, so the vector potential is like the ripple effect of the magnetic field extending beyond its immediate boundaries.
That's a good way to think about it.
And according to the Aharonov-Bohm effect, electrons are sensitive to this vector potential.
Yes.
Even if they're not physically passing through the magnetic field itself.
That's right.
So even if an electron is swimming outside the magnetic whirlpool, so to speak, it can still feel the current.
That's the gist of it.
Wow.
And Tonomura and his team designed a brilliant experiment to test this effect using their electron holography setup.
How did they actually test something so abstract? What did the experiment look like?
They used a tiny donut-shaped magnet.
Donut-shaped magnet.
Called a toroidal magnet.
Okay, why the donut shape?
The toroidal shape is key because it confines the magnetic field entirely within the donut.
So there's no magnetic field outside the donut?
There's absolutely no magnetic field leakage outside.
Ah, clever.
Yeah.
So they eliminated any chance of the electrons being affected by the magnetic field directly.
Exactly.
They isolated the vector potential as the only possible influence.
Exactly.
Okay.
They sent two beams of electrons, one passing through the hole of the donut and the other passing outside of it.
Okay.
Then they recombined the beams to create an interference pattern.
If the Aharonov-Bohm effect is real, those two beams should experience a shift in their interference pattern,
Yes.
even though one never encountered the actual magnetic field, right?
You're absolutely right.
Yeah. Okay.
And that's exactly what they observed.
Wow, so they actually confirmed the Aharonov-Bohm effect.
Yes.
That's a huge win for quantum mechanics.
It is.
Did this convince the skeptics?
Some, but not all.
Really?
Yeah, the debate continued for years, which is actually a testament to the rigor of science.
I guess so.
To address the remaining skeptics,
Yeah.
Tonomura and his team designed an even more challenging experiment.
Okay, what did they do?
They enclosed the toroidal magnet in a superconducting shield.
Wait, superconductors?
Yes.
We haven't even talked about those yet.
Right.
I know they have something to do with zero electrical resistance, but how do they fit into this story?
So superconductors have this incredible ability to expel magnetic fields from their interior.
Okay.
It's a phenomenon known as the Meissner effect.
The Meissner effect.
Yeah.
So they block magnetic fields.
By enclosing the magnet in a superconductor, Tonomura and his team guaranteed there was absolutely no magnetic field leakage whatsoever.
So it's like the ultimate magnetic invisibility cloak.
That's a great way to put it.
Not even a whisper of a magnetic field can escape.
It ensured that any observed effects were solely due to the vector potential and not stray magnetic fields.
What a fantastic way to solidify their findings.
It was.
I'm on the edge of my seat. What happened next?
The results of this experiment were groundbreaking. They not only confirmed the Aharonov-Bohm effect under incredibly stringent conditions, but also made another remarkable discovery.
What's that?
The magnetic flux trapped inside the superconducting shield was quantized.
Quantized?
Yeah.
Does that mean it could only exist in specific discrete amounts?
Exactly. It's like the magnetic flux could only take on values corresponding to specific steps on a staircase. It couldn't take on any arbitrary value in between.
Interesting.
This quantization of magnetic flux is a fundamental property of superconductors.
Okay.
And it's closely tied to the wave nature of electrons.
Okay.
Or, more specifically, Cooper pairs.
Okay, we've jumped ahead.
We have.
What are Cooper pairs?
Yeah.
What role do they play in all of this?
Cooper pairs are fascinating.
Okay.
Imagine two electrons, which usually repel each other, suddenly deciding to pair up.
That sounds counterintuitive.
It is counterintuitive, but that's the magic of quantum mechanics at play.
Electrons attracting each other.
Inside a superconductor, electrons interact with the vibrations of the material's atoms.
Okay.
Think of it as a subtle dance between the electrons and the atoms. This interaction can overcome their natural repulsion, leading to the formation of Cooper pairs.
So through this atomic tango, electrons overcome their differences and form these Cooper pairs.
Exactly.
I'm starting to see how everything is connected in this quantum world.
And these Cooper pairs are responsible for the remarkable properties of superconductors.
Okay.
They can move through the material with absolutely zero resistance, which allows superconductors to conduct electricity without any loss of energy.
So Cooper pairs are the reason why superconductors live up to their name.
Precisely.
But how does this relate to the quantized magnetic flux Tonomura observed?
The quantization arises from the wave nature of these Cooper pairs.
Okay.
Each pair behaves like a single quantum entity, and its wave function has to be single valued.
Single value.
Meaning, if you trace the wave function as it travels around a closed loop,
it must end up back where it started.
So like a snake biting its own tail, the wave function has to form a complete loop.
That's a great analogy.
Now remember that the vector potential affects the phase of the wave function.
Right.
So for the Cooper pair's wave function to remain single-valued as it travels around, the magnetic flux enclosed by that loop has to be a multiple of a fundamental quantum of flux.
Exactly.
That's a lot of technical details.
It is.
But the main point is that the wave nature of Cooper pairs forces the magnetic flux to be quantized. Right?
Precisely. And Tonomura and his team didn't just observe this quantization. They actually witnessed the process of flux quantization happening in real time.
They saw it happening.
They controlled the magnetic flux passing through their superconducting shield and watched as it jumped from one quantized value to the next.
So they could see it changing in steps.
It's like watching nature snapping to a grid defined by the fundamental constants of the universe.
That's an incredible visual.
It's really amazing how seemingly mundane things like the flow of electricity become so complex and elegant when viewed through the lens of quantum mechanics.
Exactly.
And one of the most captivating dancers in this quantum ballet is the vortex.
Ah, yes, the vortex.
You've mentioned vortices a few times now.
Right.
What exactly are they?
They're essentially whirlpools of supercurrent,
Okay.
those frictionless flows of Cooper pairs,
Uh-huh.
and they dictate how superconductors behave in the presence of magnetic fields.
Oh, how to?
Remember how some superconductors can allow a bit of magnetic flux to penetrate their interior?
Vaguely.
Well, that flux enters in the form of these quantized vortices.
Okay.
Each vortex carries a single quantum of magnetic flux,
Uh-huh.
and they arrange themselves in a regular lattice-like pattern within the superconductor.
So we have tiny tornadoes of magnetic flux spinning inside the superconductor.
Right.
And they're all neatly lined up, like
Oh.
soldiers on parade.
A vivid and accurate picture.
And the fact that they're quantized,
Yes.
each carrying exactly one quantum of flux,
Yes.
is yet another testament to the wave nature of those Cooper pairs.
Exactly.
It's mind-boggling that we can actually observe these quantum tornadoes using electron holography.
It is.
What other insights did Tonomura gain from studying them?
He witnessed all sorts of fascinating behaviors.
Like what?
For instance, he saw vortices annihilate each other
Annihilate each other.
when they collide with those spinning in the opposite direction.
Wow.
It's similar to matter and antimatter particles disappearing in a flash of energy,
Okay.
but on a much larger scale.
So like miniature Big Bangs occurring within the superconductor.
You could say that.
It emphasizes that these vortices aren't just abstract mathematical constructs.
Right.
They're real physical entities
Yes.
with their own unique properties and behaviors.
It's a remarkable thing to see.
Thanks to electron holography,
Yeah.
we're witnessing a whole new world unfolding before our very eyes.
We are.
What other wonders did Tonomura uncover on his quantum expedition?
He found that these vortices aren't always stationary.
They move around.
They can move around inside the superconductor,
Okay.
especially when the temperature is close to the point where the material transitions between its superconducting and normal states.
So those soldiers on parade can actually break formation and dance around.
Precisely.
And their movements are influenced by various factors like
Yes.
defects in the material, temperature differences,
Right.
and even the presence of other vortices.
It's an intricate choreography,
It is.
orchestrated by the interplay of quantum mechanics and electromagnetic forces.
I imagine observing these movements provided even more insights into the behavior of superconductors.
Absolutely.
So it's not just about the fundamental physics.
Right.
It has practical implications for creating better superconducting materials and devices.
Exactly.
The knowledge we gain from observing these quantum dances could lead to breakthroughs in a wide range of technologies,
Yes.
from more efficient power transmission to faster and more powerful computers. It's truly remarkable how something as seemingly abstract as the wave nature of electrons can have such profound real-world consequences.
That's the beauty of fundamental research.
Yeah.
You never know where it will lead.
True.
Tonomura's work highlights the importance of pursuing scientific curiosity, even if it takes you down unexpected paths.
Speaking of unexpected paths,
Yes.
we discussed vector potentials earlier in the context of the Aharonov-Bohm effect.
Right.
You mentioned that some physicists initially dismissed them as just a mathematical tool, a convenient fiction,
That's true.
but Tonomura showed they have a measurable effect on electrons.
Yes.
Does that mean vector potentials are more than just a mathematical abstraction?
It's a question that has puzzled physicists for over a century,
Wow.
and Tonomura's work definitely reignited the debate.
Okay.
The Aharonov-Bohm effect strongly suggests that vector potentials have a physical reality,
Uh-huh.
at least in the quantum world.
So in the quantum realm, vector potentials are a real deal.
Yeah.
What about our everyday macroscopic world? Do they hold any significance there?
That's still a topic of exploration.
Okay.
Some physicists believe vector potentials might play a role in explaining macroscopic phenomena like superfluidity and even gravity. But more research is needed to confirm these ideas.
So the story of vector potentials is still being written.
It is.
It's fascinating how something once considered a mere mathematical convenience could turn out to be a fundamental aspect of reality.
It underscores the ever-evolving nature of science.
Right.
What we think we know can be completely transformed by new discoveries and insights.
Okay, I need a moment to process everything we've discussed.
Yeah.
From electron waves and quantum tunneling to Cooper pairs, quantized vortices, and the enigmatic vector potentials.
We've covered a lot.
It's been a whirlwind tour of the quantum world.
Indeed.
And we've only just begun to unravel the mysteries of this fascinating realm.
We've only just scratched the surface.
Well, before we delve further,
Okay.
I think this is a good point to take a short break.
Yeah, good idea.
Give our listeners a chance to digest all this incredible information.
A quantum coffee break, perhaps.
Exactly.
Yeah.
We'll be back soon to wrap up our exploration of the quantum world and discuss some of the implications of Tonomura's work for the future of science and technology. Welcome back to our deep dive into the quantum world.
Yes.
It's been an incredible journey exploring the work of Akira Tonomura.
It has.
We've covered some truly mind-bending concepts, from electron waves and quantum tunneling to the intricate world of Cooper pairs and quantized vortices.
Yeah.
We even ventured into the mysterious realm of vector potentials.
Lots to think about.
It's been an amazing ride through the quantum landscape.
For sure.
You know, one thing that really struck me while reading Tonomura's work is his sheer passion for revealing this invisible world.
Yeah.
His drive to make the quantum realm accessible to us. There's a real sense of wonder and awe in his writing.
Absolutely.
He talks about wanting to show the world the strange behavior of those magnetic vortices, to share the sheer strangeness of it all.
Right.
He's not just a scientist.
Yeah.
He's an artist using electron holography as his paintbrush to reveal these breathtaking images of the quantum world.
I like that analogy.
It reminds me of those early astronomers gazing at the night sky for the first time,
Oh, yeah.
awestruck by the vastness and complexity of the universe.
Yeah.
Tonomura's work is doing something similar, but at the opposite end of the scale,
Right.
revealing the hidden intricacies of the microcosm.
And just as those astronomical discoveries revolutionized our understanding of the cosmos, Tonomura's research is reshaping our understanding of matter and energy at the most fundamental level.
So where does this quantum revolution lead us?
Well,
What are the potential implications of Tonomura's work for the future?
the possibilities are vast.
Like what?
His insights into the behavior of vortices and superconductors could pave the way for more efficient and powerful superconducting devices.
Can you give us some examples of these devices?
Sure.
What could this technology look like in practice?
Imagine power grids that can transmit electricity with virtually no loss,
Okay.
leading to incredible gains in energy efficiency.
That would be huge.
Think of ultra-fast computers that operate with minimal energy consumption,
Wow.
or incredibly sensitive magnetic sensors that could revolutionize medical imaging and materials analysis.
Interesting.
These are just a few glimpses into the transformative technologies that could emerge from a deeper understanding of superconductivity.
That's an exciting future.
It is.
We're on the verge of a technological revolution driven by the magic of quantum mechanics and superconductivity.
It's an exciting time.
But it's not just about the practical applications, is it?
You're right.
Tonomura's work also compels us to re-examine our fundamental assumptions about the nature of reality. The Aharonov-Bohm effect, for example,
Yeah.
challenges our traditional notion of locality, the idea that an object can only be influenced by forces acting directly upon it.
It brings to mind that concept of spooky action at a distance that Einstein grappled with.
Exactly. The fact that electrons can be influenced by a magnetic field they never physically encounter
Right.
hints at a deeper level of interconnectedness in the universe than we previously imagined.
Absolutely.
It's a mind-boggling concept,
Yeah,
but also incredibly exciting.
it is.
We're peeling back the layers of reality and finding a world that operates by rules that are both strange and beautiful.
It's a strange and beautiful world.
It's remarkable to think that our journey started with a simple question. How can we see magnetic lines of force inside a magnet?
And it's taken us far.
And it led us to explore some of the most profound mysteries of quantum mechanics.
It's a testament to Tonomura's brilliance and unwavering curiosity that he was able to unveil so much of this hidden world.
Absolutely.
If Tonomura could use electron waves to make the invisible visible, what other marvels are waiting to be discovered? What other quantum dances are playing out at the subatomic level, waiting for us to develop the tools to observe them?
Those are great questions to think about. These are the questions I'll be pondering long after our deep dive is over.
Me too.
We've only just begun to explore this fascinating topic.
Yeah.
If you're eager to learn more, we highly recommend diving into Akira Tonomura's book, The Quantum World Unveiled by Electron Waves, to continue your own exploration.
It's a great book.
Until next time, stay curious.